Welcome everyone to this highly technical deep dive. We are structuring this a bit differently today, basically treating it as a professional slide deck presentation for you all.
Yeah, we're really getting it into the weeds on this one.
Exactly. So our mission overview today, we are analyzing the engineer's field guide to the Mohs scale. The goal here is to translate Friedrich Mohs' 1812 field assessment into modern crushing, metallurgy, and energy decisions. Okay, let's unpack this.
It is honestly an incredible translation of data. Like, we're taking a purely qualitative observation from the field, and linking it directly to massive quantitative engineering outcomes.
Right. So on this slide, we examine the origin and the 30-second triage.
Which is really about the ordinal scratch protocol.
Basically, you just take an unknown sample and a reference mineral. And if the sample scratches the reference, it's harder.
Yeah, that's the whole foundation. And the specifics of the field tools are wonderfully low tech. I mean, a Mohs 2.5 is literally just your fingernail.
Just a fingernail. Oh, wow.
Yeah. And then a 3.0 is a copper coin, which covers your calcite-grade minerals, and a 6.0 is just a standard steel file.
But there is a catch here, right? Because the guide mentions this polymineralic caveat.
Oh, right. You absolutely have to factor that in. Rocks are composites. They aren't just one single pure mineral.
So they have different phases.
Exactly. So if you are evaluating a polymineralic rock, like granite, its overall wear behavior isn't some average of its soft and hard parts. It's actually driven almost entirely by its hardest dominant phase.
Usually the quartz, right?
Yeah, usually the quartz.
So it's kind of like a chain, but, in reverse. Instead of the weakest link dictating the overall strength, the absolute hardest grain dictates your equipment wear.
That is a great way to look at it. That hardest grain does all the real damage.
Moving to the next slide, we hit the severe wear threshold.
Right, and this is where we really have to contrast Mohs with Vickers. Because Mohs is just an ordinal field triage, but Vickers is absolute hardness.
Like a laboratory measurement.
Exactly. It measures exactly how much physical force it takes to dent the rock. And if you look at the data, the Mohs scale is wildly nonlinear.
Yeah, I mean, going from talc at Mohs 1 up to apatite at Mohs 5 is like walking up a gentle hill. The Vickers numbers barely rise at all.
But then you take the step from Mohs 6 to quartz at Mohs 7, and it's like suddenly running into a vertical brick wall.
It just spikes dramatically, right? To roughly 1,100 Vickers.
Yes. And by the time you reach diamond at Mohs 10, it skyrockets to 10,000 Vickers.
That is insane.
It is. And that Mohs 7 spike is the ultimate engineering consequence here. Because at Mohs 7, standard carbon steel actually stops being harder than the rock it's trying to break.
Wait, really? So quartz will literally blunt and spark against standard tool steel?
Well, absolutely.
So at Mohs 7 and above, standard steel just becomes completely uneconomical for plant liners.
Completely uneconomical. Your machinery would basically be destroying itself.
So how do you even physically break something that destroys your steel?
Well, you have to engineer a response.
Which brings us here. Moving to the next slide. We bridge hardness to physics and equations.
Right. The guide maps out this whole decision tree based on hardness bands.
So for Mohs 1 through 3, stuff like limestone, you'd use impact crushers. I kind of picture those functioning like taking a baseball bat to a sheet of glass.
Yeah, that's a great analogy. And for that baseball bat approach, you equip the crushers with chrome-molybdenum liners.
Because they handle the abrasion of softer rocks perfectly.
Right. But try taking that same baseball bat to a massive boulder of quartzite at Mohs 7.
The bat just shatters.
Exactly. Impact becomes economically impossible at that point. So the guide mandates compression machines for anything Mohs 7 and up, jaw and cone crushers.
So instead of a bat, these act more like a giant, relentless nutcracker.
Yes. And the metallurgy has to change too.
Yeah.
You have to utilize 18% manganese Hadfield steel for these compression crushers.
I was wondering about that specific steel. Why Hadfield?
Because it actually work hardens under impact.
Wait, what does that mean?
It means every time a huge rock smashes into it, the immense pressure alters the steel's crystalline structure. It forces the surface molecules into a tighter lattice, making the metal harder and more resistant the more it gets battered.
Oh, wow. So the rock literally beats the machine into becoming stronger.
It's brilliant metallurgy, but there's a contextual call-out we need to make here regarding the energy.
Right, because Mohs tells us what family of crusher to buy. But there are no equations in the Mohs scale.
Exactly. To figure out the specific energy and the actual size of the multi-megawatt motor you need, engineers have to rely on the bond work index equation.
Okay, so summarizing this for you all, every single kilowatt hour in these massive operations traces back to this simple hardness triage.
Right.
You use a fingernail or a penny scratch test to eliminate incorrect crusher families. You respect the exponential wear above Mohs 7 by switching to compression machines. And you use the bond work index to size your throughput.
It really just proves that the most advanced aggregate engineering heavily relies on the fastest, simplest field assessments to set its baseline.
Which leaves you with this provocative thought to mull over. If a 200-year-old fingernail and penny scratch test still strictly dictates multi-million-dollar metallurgical and energy decisions today, what other ancient low-tech heuristics are quietly running our modern high-tech industries?